Okay. So where there will be increase in net length, breadth, that is area or superficial expansion. Then if the metal involved is a 3D where we have its length, width, and height, something like this. At least what I have in my hand, we have one side of it, another side, and then the thickness, which is its height. Something like this will go through volume expansion, meaning there will be an increase in its length, its breadth, and then the height. Okay. So that is what we are trying to, or what it means by linear expansion, area or superficial expansion, volume or cubic expansion. All right. And yesterday, I'm coming in. Okay, yesterday we derived a special relationship between, okay, so we came to a quick recap whilst we wait for your people. We came to the realization that if you have a length L, an initial length L naught at temperature T, initial temperature T. If this is subjected to a change in temperature, let's assume the initial temperature is 0. So at a temperature of 0 degrees Celsius, initial temperature, when the metal is heated, it goes through expansion. So the change after the change in temperature would be L2. Let's assume after it's being heated, the metal increased to a length like this. So this whole length is L1, final length after it being heated, meaning that the increase or the change is this distance, or yes, that is delta L, small change there, meaning that L2 meaning that L1, which is the final length, will be equal to L naught plus delta L. Okay, delta L, we realize, is directly proportional or is equal to the coefficient of linear expansivity or expansion alpha times the original length times the change in temperature. So this is actually, assuming this is T, the change in temperature is actually T minus 0. Therefore, the final length L2 is equal to alpha L naught times delta T plus L naught. We factorize out the original length and had 1 plus alpha delta T. So this gives us an expression of the final length. This is the final length. Alpha is the coefficient of linear expansion, meaning the change, okay, the change in the length per unit length per degree or Kelvin rise in temperature. That is the definition of alpha. Okay, the change in length per unit length of the substance or body or material per Kelvin or degree rise in its temperature. So if a material has a coefficient of linear expansivity to be 0.01, what it means is that the change in length per unit length, okay, of the material per any Kelvin rise or degree rise in its temperature is equal to 0.01, meaning at an increase or change in temperature of 1 Kelvin or 1 degree Celsius, the material increases or expand by 0.01 meter length. That is basically. Then we looked at area expansion. If we have a two-dimensional figure, length, breadth, and we came to the realization that, okay, here change in the area is equal to that constant of proportionality times the original cross-sectional area A naught times delta change in temperature T final minus T initial. This we realize that the constant of proportionality is the coefficient of area expansion beta. So K is equal to beta A naught times change in temperature delta T. So please, this is always a change in temperature, a final minus the initial. So don't make the mistake to take it as just T. Okay, we'll be solving questions. So then we came to conclusion that coefficient of area expansion is equal to 2 times the coefficient of linear expansion. Meaning for a two-dimensional figure, it expands twice. Okay, so if alpha is 2, beta will be 4. All right. Please let me take a quick shot and drop attendance. Okay. The attendance isn't encouraging to me. So let me take a shot and upload it. Back. So beta is that. Then we started with volume or cubic expansion in solids. Volume or cubic expansion in solids. So this applies to anything three-dimensional. Hello. Oh, hey, Charlotte, I've uploaded notes on the platform.
Oh, okay. Thank you.
So here there will be increase in the length, the breadth, and then the height of the objects. So this time around, a 3D, three-dimensional figure would go through a triple expansion. Okay, and so this is the original volume of this V naught at an initial temperature T. So after, yes, I asked you to prove this, and in fact, a lot of you were able to kill it. Okay, a round of applause to your own self. A lot of you did very well with this. Prove that cubic expansion is equal to 3 times the linear expansion. So after a temperature T, after a final temperature T, the volume, there will be an increase in the volume because the length would increase, the length L naught, the breadth V naught, and then the height H would all increase. Okay, and so the change in volume, okay, I even did that here. The change in volume is equal to this. The original volume is directly proportional to the original volume times the change in temperature. Therefore, when we introduce an equal to in order to establish an equation, the change in volume is equal to the constant of proportionality, which we are calling as, so alpha here refers to the coefficient of volume or cubic expansion. So that constant of proportionality K is equal to gamma, which is the coefficient of alpha. So the new volume V1 would be equal to the initial volume V naught plus the change in volume after expansion. The change in volume after expansion. Therefore, we have V naught plus gamma times V naught times delta T. And the new volume also becomes V naught out 1 plus gamma delta T. This is the expression for the final volume after expansion. Final volume after expansion. Then we came to establishing the relationship between linear expansivity and cubic expansivity, where after a temperature T1, we realize that the new length L1 will be equal to old length L0 plus the change. The change in length is alpha L0 delta T. Then the new width, which is B1, would also be the original width or breadth B0 plus alpha B0 delta T. Then the new height after the expansion, HI, will be equal to original height plus alpha HI times H0 times delta T. Therefore, the final volume V1 will be equal to L1 times B1 times H1. Then you put in whatever you have here. So we'll have V1 equal to L0 plus alpha. Let's even factorize L0 out, 1 plus alpha delta T times B1. B1 would be equal to B0 times 1 plus alpha delta T times H1. H1 is also H0 times 1 plus alpha delta T. Then the rest is mathematics. V1 therefore is equal to L0 times V0 times H0 all times 1 plus alpha delta t all raised to the power 3. When you expand this binomial, you have a naught. This product gives us the original area. Expansion of this is 1 plus 3 alpha delta t plus 3 times alpha squared delta t squared plus 3 raised to the power 3 delta t to the power 3. And this part and this part all goes to 0.
This is volume, not area.
Hey, thank you for seeing mistake. Okay, so all this part goes to 0 because as you raise the power of linear expansivity, they get close to 0. So you have V1 times V naught times 1 plus 3 alpha delta t. Then you compare this to this one, this expression of final volume. When you compare, the conclusion is that you have V naught times 1 plus gamma delta t equal to V naught times 1 plus 3 alpha delta t. Okay. So V naught cancels out, and you have this going reducing to 0. So you have alpha delta t is equal to 3 alpha delta t. 3 alpha delta t. So that change in temperature, and you have gamma equal to 3 times alpha, meaning cubic or volume expansion. Volume expansion is equal to 3 times linear expansion. That's the show. So if a body increases linearly by 3%, its cubic expansion will be 9% because volume expansion is 3 times linear expansion, and that is all. Please, any question? But as I said earlier, a lot of you were able to do this out. Okay. We'll look at expansion in liquids. Expansion, because this is all about expansion in solids. Let's try solving the question. First, we look at the question I earlier gave to you yesterday. The question forwarded to you yesterday. Can I clean it? Yes. It's in the note, so you don't worry. Your question says that I want to retrieve it and then okay. A metal rod of coefficient of linear expansion 0.001 per Kelvin. So its coefficient of linear expansion alpha is equal to 0.0001 per Kelvin. It's heated from 0, so T initial is 0 and T final 100 degrees Celsius. Calculate the percentage increase in length. Percentage is fraction. Change in length per the original length. Okay, so change in length L, which is alpha times original length times delta T. So the delta L, change in length, is equal to 0.0001 times the original length times a change in temperature of 100 degrees Celsius or 100 Kelvin. Don't forget, for change in temperature, the ratio is 1 K is to 1 degree Celsius. So a change in temperature of 100 degrees Celsius is also equal to 100 Kelvin. So this is equal to 0.01 times the original length. This is delta L. Therefore, percentage change in length or percentage delta L will be equal to delta L over L naught times 100%. L naught, this is equal to 0.01 times L naught over L naught. So obviously, L naught cancels out, and you have it to be equal to 1%. So the percentage change in the length would be equal to 1%, as answered by a lot of you. Okay, another question. I'm reading the question out, a trial question out to the house to enjoy. Are we ready? Hello, are you ready?
Yes, please.
Yes.
The coefficient of linear expansion of ion. The coefficient of linear expansion of ion is 0. I'm coming to write the coefficient of linear expansion. So we are told that the coefficient of linear expansion of ion is 0.00012 per Kelvin. Per Kelvin. 0.00012 per Kelvin. Explain the meaning of this statement. So explain the meaning of this statement that the coefficient of linear expansivity or expansion of ion is that. Then calculate the superficial expansion and then the cubical expansion. So I calculate the superficial and cubical expansion of ion. 3 minutes. 3 minutes. Are we through?
For everyone, 1 meter of iron, the length of iron increases by 1.2 times 10 exponent minus 5 meters per 1 degree Celsius
That
temperature change.
for every what?
1 meter of the iron. The length of the iron increases by 1.2 times 10 exponent minus 5 meters per 1 degree Celsius temperature change.
Okay, let's also hear from one of the gentlemen. And I think Festus, what do you also think? What does the statement mean?
So for every 1 meter of the ion, the change in length per unit Kelvin rise in temperature of the ion is 0.00012 per Kelvin.
Okay, so the change in length per unit length, one, and that's what you say, 1 meter. Per a Kelvin or degree Celsius rise in temperature is equal to 0.000012 meter. So when you subject 1 meter length, okay, of iron to a temperature change of 1 Kelvin or 1 degree Celsius, it will expand by this amount. Okay, we have to calculate the superficial and cubical expansion of ion. How did we solve this? First, let's listen to Natalie. Natalie, how did you solve for the superficial expansion?
I only did the cubical expansion.
Okay, so how did you do that? How did you calculate for the cubical expansion? Oh, Natalie, are you gone?
So the coefficient of m. Okay, so since can you hear me?
Yes, I can. Natalie, I can hear you.
Can you hear me?
Yes, I can. All right, let me take over because of time. Okay, so since alpha is given as 0.000012 per Kelvin and beta area expansion or superficial expansion is 2 times linear expansion. This is 2 times 0.000012. Okay, and this will be 0.000024. Okay, per Kelvin or per degree Celsius. Then volume or cubical expansion is also 3 times linear expansion. So 3 times 0.000012, which will also give us 0.000036 per Kelvin or degrees Celsius. So simple. Another trial work. Another question. Another question. A metal rod has a length of 99.4 centimeter at 200 degrees Celsius. At what temperature will its length be 100 centimeter? A metal rod has a length of 99.4 centimeter at 200 degrees Celsius. At what temperature will its length be 100 centimeter? If the linear expansivity of the metal is 2.1 times 10 to the power -5 per Kelvin. At what temperature will its length be 100 centimeter? If the linear expansivity of the metal is 2.1 times 10 to the power -5 per Kelvin. This is your question. So 5 minutes.
Mr. Asia,
Hello.
please, you said the rod length is what?
99.4 centimeter.
Okay, thank you.
Then the linear expansivity is 2.1 times 10 to the power -5 per Kelvin. Let me have your question again. Okay, so I'm repeating the question. A metal rod has a length of 99.4 centimeter at 200 degrees Celsius. At what temperature will its length be 100 centimeter? At what temperature will its length be 100 centimeter if the linear expansivity of the metal is 2.1 times 10 to the power -5 per Kelvin? Eura, are you through? Eura,
My line kept on breaking.
come again.
My line kept on breaking.
Oh,
Like my connection is unstable, so I didn't hear the question.
okay, let me send it to you. I'll send the question to you. An iron bar of length 10 meter is heated. So the original length is 10 meter. L is 10 meter. The change in temperature is 100 degrees Celsius because the initial is 0. If the coefficient of linear expansion of iron is, so we are given the linear expansivity of iron to be 1.0 times 10 to the power -4 per degree Celsius. We have to calculate the increase in length of the bar. Yes, Natalie?
So please, can I say the answer or you want to solve it?
I want us to solve, so you mark yourselves.
Okay.
Okay. So change in length is equal to the linear expansivity times L naught times the change in temperature. That's all. Okay. And so 1 times 10 to the power -4 times 10 times 100. So 0.1 meter, I guess. Is that what you got?
Yes, please.
All right.
Yes, sir.
All right. Take your assignment. Put your assignment question down before we begin with expansion in liquids. The density of a metal is 8.9 gram per cm cube at 0 degrees Celsius. The density of a metal is 8.9 times 8.9 gram per cm cube at 0 degrees Celsius. Find its density at 20 degrees Celsius, find its density at 20 degrees Celsius if its linear expansivity or linear expansion is 2.0 times 10 to the power negative 5 per Kelvin. The density of a metal is 8.9 gram per cm cube at 0 degrees Celsius. Find its density at 20 degrees Celsius if its linear expansivity is 2.0 times 10 to the power negative 5 per Kelvin. Amma,
Mr. Adria, please see the question you gave us about superficial expansivity. You used area expansivity formula. So does it mean that superficial expansivity is the same as area expansivity?
exactly. And volume expansivity is the same as cubic.
Okay. What of the linear?
As for linear, it is just linear.
Okay.
Okay. So we know that temperature affects density. One of the factors which affect density has to do with volume and temperature. So you are given the initial density of a body, and then as its temperature changes from one temperature to another, you are asked to calculate the density, the new density of the same material or body if its linear expansivity is given or provided as such. Okay, this is a question I want you to think around. How would you relate density to this linear expansion thing? Think through, read around, and let's see what you can be able to produce. All right, so that's your assignment. Now, expansion in liquids. Thermal expansion in liquids. Solid goes through three. Solid goes through three of those expansion: linear, area, and volume. Liquids do not go through linear, area. They only go through volume expansion. Liquids and gases generally, they go through volume or cubical expansion. Okay, this is because liquids and gases have volume. They don't have length, no breadth, and so there wouldn't be anything, but they have volume. So they only go through volume expansion. Okay, I've sent you abridged or shortened notes on expansion in liquids. So please check on the page. Check on the page. I've given you notes on expansion in liquids. So it is well-crafted notes, self-explanatory. So I want you to spend time, read through. As you read through, if there are areas you are not clear, you'll let me know. Okay. And liquids have two coefficients of volume expansion. That is real and then apparent. So, and the relations or formula involved, I've given it to you. So spend time to read on this so we can do something else. Let us look at abnormal expansion of water, or anomalous, still on expansion in liquids, but I want us to look at anomalous or unusual expansion of water. Anomalous, some term this adjective as abnormal. Yes. Why is it anomalous? Why is it abnormal? It is abnormal because you see, all substances are such that when you supply heat, when you add heat energy to them, they would expand. So if you pick aluminium, when you heat it, it would expand, meaning the volume would increase as it gains heat energy. Even water, when you heat it, you realize that the volume would be increasing. Okay, so all substances or materials are such that as they gain heat, they expand. As they lose heat, they contract. Losing heat means that you are taking heat energy out of it. So when you have hot food and you put it in a freezer, what happens is that the freezer extracts the heat energy out of it and then throws it outside. That is why when you pass behind a fridge, okay, the air blown around feels very warm, meaning that it is the heat energy that is extracted from whatever is within the freezer and is blown out of the room. Okay, so when you cool substances, they will contract. Okay, they will contract, and at a point in time would change states. So the energy, the internal energy is taken out, thrown out. So all materials are such that as they gain heat, they expand. As they lose heat, they contract. But water obeys this norm, okay, to a certain temperature, and from there will disobey this natural law. That is why we describe water as anomalous or unusual. This behavior as anomalous or unusual expansion in water. So all substances, let me give you some information. All substances expand. This is all increase in volume when heated. And contracts as they lose heat energy. However, water obeys this norm till a certain range of temperature is reached. And starts to disobey this norm. Now, what is this temperature? Let's assume this is water molecules at maybe 10 degrees Celsius. So as heat is extracted, because this brings about pulling the molecules together, the volume of water will begin to decrease. Or it will contract, the molecules contract. So what are we doing? We are extracting heat energy out of it. So water shrinks or contracts. So 10 degrees Celsius, 9, 8, water will be contracting. Okay, contracting as we extract. Now, when it gets to a temperature, let's assume this is 9 degrees or even 6 degrees Celsius. Then when we get to a temperature of 4 degrees Celsius, even though we are extracting heat energy out of it, which we expect water to contract, water will cease to contract starting from a temperature of 4 degrees Celsius. 4 degrees Celsius, water, instead of contracting, is expanding. So at 4 degrees Celsius, instead of contracting, meaning reducing in volume, water expands. Even though heat energy is being extracted, so it begins to disobey the natural cycle at 4 degrees Celsius. Class, are you okay? Hello, are you there?
Yes, sir.
So
Yes, sir.
what happens is that the unusual behavior of water starts from 4 degrees Celsius, continues till temperature of 0 degrees Celsius. Then, instead of this is expanding, then it will begin to contract. So the abnormality actually ends at 0 degrees Celsius. Now, when you are heating, here we are extracting heat energy out of it. Okay, when we are actually supplying heating water, the same thing. When you heat a substance, the natural or the norm is that it must expand. So maybe at a temperature of give me any temperature. At a temperature of 3 or 1 degrees Celsius, and we are adding, this is water at 1 degrees Celsius. As we heat, we expand, we expect that the molecules, okay, expand, and so the volume would increase. So as we heat substance, it must expand. This natural norm will be obeyed continuously, okay, as the substance is heated. But when it is heated and gets to 4 degrees Celsius, this abnormality also comes in. Instead of water expanding, it rather contracts at 4. So usually what we do is that we pick ice. In demonstrating this, we pick ice at maybe negative something. Ice at maybe negative 5 degrees Celsius and heat it. So as we heat ice, it will gain energy and then expand. Okay, it will expand, obey the norm. But the moment the temperature reaches 4 degrees Celsius, as temperature reaches 4 degrees Celsius, instead of ice expanding, it will be contracting. It will contract on and on and on. So this is the abnormal expansion of water, where the abnormality starts from 4 at a temperature of 4 degrees Celsius. Okay.
Yeah.
Please, any question?
Yeah.
Hello.
Yeah, please, when it gets to 0 degrees Celsius, won't it turn into water?
Come again.
When the ice is heated to 0 degrees Celsius, won't it turn into water?
So what happens is that, yes, it is ice at -5, -5, 0, -4, 3. When it gets to 0, change of state will start. Okay, so this change of state will start. So what actually happens is that expansion, okay, from as we heat it. Then when it gets to 0 to 4, instead of it expanding, then it contracts. So the change of state actually starts from 0 and then also ends at 4, just as when we are heating it, it is from 4 to 0. So this contraction start at 0, ends at 4. Start at 4, ends at 0. So this is what happens. Yes, at 0, change of state will happen. Ama.
Mr. Adria, please, are you saying that when water is heated, when it reaches 4 degrees Celsius, it has to contract, and when it is being cooled, when it reaches 4 degrees Celsius, it has to expand?
Exactly. The whole idea is that as we heat, it is from negative. So as it absorbs heat, okay, it is absorbing heat, it must expand. But naturally, what happens is that it will expand, but when it gets to 0, instead of it expanding, even though it is gaining heat, it would contract, okay, and go on and on till when it gets to 4 degrees Celsius. Then when you are cooling, in cooling, we expect water to contract, okay, it will be obeyed, but when you cool it to 4 degrees Celsius, that is when it begins to rather expand. So the abnormality when you are heating starts from 0, ends at 4. When you are cooling, starts at 4, ends at 0. Are you okay?
Yes.
All right. Now, you see, this anomalous expansion of water practically is the reason why when water is put in a freezer and is frozen, okay, when it changes state from water to ice, its volume increases even to the extent that it can break the glass, whatever the ice is into it. Because at 0 degrees, okay, so once it's in the freezer, it is being cooled. At 4 degrees Celsius, instead of water expanding, no, instead of water contracting, it is expanding at 4. Okay, this expansion will continue. Don't forget, at 4, we still have liquid water. 3, 2, 1 to 0. At 0, change of state from liquid to solid starts. Okay, now change of state occurs at a constant temperature. So at 0, it will go on and on and on till it will still be 0, till every water has turned to ice. By then, the water has expanded so much that it can hardly be contained in its way, okay, in the container, if it is smaller. So that is why when you put water in a freezer and you fill it, you fill the bottle or whatever is containing it to the full. When it changes state, it can even break, okay, the container because of the anomalous expansion of water. So it will change, the expansion of water will cease when every water has changed to ice. But by that time, if you filled it to the fullest, it has already expanded and has damaged the container. Please, are you okay? Please, any question? All right, so this is the concept of anomalous expansion of water. Now, this anomalous expansion of water in very cold regions has some positives or benefits to aquatic life. So let's look at how anomalous expansion of water is beneficial to very, very cold regions, okay, of the world, and how it protects or benefits aquatic lives. So how anomalous expansion of water help preserve aquatic lives during winter. So let's take this to be a pond. This is the surface of the pond. Now, during winter, the temperature of the surrounding is being cooled. So it is like similar to having placed an object in a freezer. Okay, it will be cooled. And when cooled, heat energy will be extracted out of it. So let's assume that we are starting from when the temperature of the weather is 10 degrees Celsius. So because during winter, the temperature of the surrounding is cooled from 9, 8, what happens is that the surrounding is being cooled, the water body is being cooled. when it drops and gets to 4, don't forget that the immediate surface of the pond experiences the change in weather. So at 4 degrees Celsius, let's assume this is the layer that feels the change in the weather so much. It can affect all the volume of the water because the mass is huge. But let's assume this is the layer that is affected by the change in temperature. So we have water body experiencing an change in temperature of 4 degrees Celsius. One may ask, why are we so critical at 4 degrees Celsius and not 9, 8, 7, and so on and so forth? The thing is that, you see, we said that water contracts, water when cooled must contract, okay? When cooled must contract. Now from 4, at 4 degrees Celsius, we have the minimum volume of water occurring, and we have the minimum volume and maximum density occurring. So at 4 degrees Celsius, we have the maximum density of water. Let me explain this again. You see, water contracts as we cool it. Density is equal to mass over volume. So at different temperatures, the volume of water is changing. Okay, 9, 8, volume, the water is contracting. 7, it is contracting. By the time it gets to 4, where the abnormality starts, we have the minimum volume of water occurring. Please, are you following? Class, are you following?
Yes, sir.
So at 4, water has contracted or shrinked, and we have its minimum volume occurring. The minimum volume implies that then density of water will be maximum at that temperature, 4. So water has its maximum temperature at 4 and its minimum volume at 4 as well. So if its density is maximum at 4, then it means that at a temperature of 4 degrees Celsius, water has the heaviest density. So if this section experiences temperature at 4, then among all the layers or the segments of water, it will be the most dense section. So what happens is that because water is heavier at 4, it will displace all the volume layers of water and come and settle below. Don't forget that for liquids, when one liquid is denser than the other, the less dense liquid settles on the most dense liquid. So because at 4 degrees Celsius, at this temperature, water is denser, okay, it will topple or displace all the sections, parts of the water, and then that will settle below. The less dense section of the water will come up. Now the temperature drops to 3. 3, the density will be less than density at 4, because at 3 degrees Celsius, water is expanding. The anomalous ends at 4, but from 3 degrees Celsius ongoing, water will be expanding instead of contracting. So if density at a temperature of 3 will be less than density at 4, so it will come and settle on it. Then at 2, the same thing. water is still expanding. Then at 1, it will come and settle on. By the time the temperature of the surrounding gets to 0, water begins to freeze. So at 0, water begins to freeze. Don't forget, at 0, we have water and ice, okay, coexisting. Okay, so the change of state from water to ice will start at 0 and will also end at 0. By the time we have complete 0 degrees Celsius solid water, we have the top part of the water body or the pond completely frozen. By then, because we have segments of water at different temperatures below, fishes and aquatic lives can come and then hide down here so that they will not be killed by the frozen topmost part of the water. This is how anomalous expansion of water preserve aquatic lives during winter. Please, if you have any question, quickly ask. Guys, I'm inviting questions from you if you have any. Yes, Festus.
Sir, please, you said at 4 degrees Celsius,
Yes.
water experiences its minimum volume.
It has its minimum volume and maximum density.
And you said at 3 degrees, it begins to expand.
Yes.
So I wanted to ask if it's that same volume that has experienced its minimum, like it's at its minimum value.
Yeah.
That's it. Is that same volume that's expanding?
Good. You see,
or like
the weather temperature is dropping during winter. So the norm is that as heat energy is extracted, water must shrink, reduce in volume. So at 10, at 9, at 8, 7, 6, because the temperature is dropping, water is contracting. The same water would contract at 9, at 10, 9, 8, 7. By the time it gets to 4, it has contracted to the least. Festus, are you following? The same water. By the time it gets to 4, it has contracted to the minimum volume, because as water continues, temperature continues to drop, it shrinks or contracts. So by the time we get to 4, we have the minimum volume of water. Festus, are you okay?
Yes, so that minimum volume will start to expand again.
Exactly. So that minimum volume obtained at 4, at 3 will begin to expand instead of contracting.
Okay.
So
thank you.
by the time we get to 4 degrees Celsius, minimum volume would bring about maximum density. So if the topmost part of the water, which experiences temperature at 4 degrees Celsius, will be heavier. And once it is heavier, it has to settle below, because liquids are such that when they have varying densities, the less dense liquid will settle on the more dense liquid. So we'll have water with different density at 4, which is the heaviest in all. Then at 3, the same volume of water now will be expanding. Okay, water being expanded means that its density will drop. So the density of water at 3 degrees Celsius will be less than this. At 2, it will at 2 will still be less than compared to 3. 1. Now, by the time it gets to 0, the temperature of the environment gets to 0, ice begins to form because change of states. Okay, but please, change of states does not, when you put water in a freezer, we don't have complete ice when the temperature is at 0. No, it starts at 0 and every change of state occurs at a constant temperature. So the temperature will not change. It would only change when every liquid has turned to ice. So at 0, the temperature will be maintained till every ice has turned to ice. So we have water at 0 and complete ice at 0. By then, we have solid ice on the surface. If fishes are here, they will be killed by the cold nature of. So they will rather run to below the pond where the temperature is at 4, which will warm them up. So they will be hiding here till maybe the summer or whatever season begins to come. So this is how the anomalous expansion of water preserves aquatic lives during winter. If there is any other question to ask from any one of you. Charlotte, Adoma and Co. Ama, are you okay?
Yes, sir.
Akuya.
Please.
All right. So that is anomalous expansion of water. Ama.
Yes, sir.
In summary, can you explain to us a lady does so, and then I'll fall on another guy to give me a summary of what we have talked about under anomalous expansion of. What is it? What is anomalous expansion of water? Ama, just tell me what you've learned about anomalous expansion of water.
Okay, sir. Please, I learned that Sir, please, I learned that water response to temperature changes is very abnormal. Yeah. So water, when it's being heated, it will be expanding, but when it reaches 0 when it reaches 0 degrees
So
Celsius.
when you are heating it, then you must pick ice that is being heated. Okay.
Yes, sir. Okay, so when water is being heated, it will be expanding, but when it reaches 0 degrees Celsius, it will contract. So it reaches 4 degrees Celsius, then it will begin to expand again. But yes, but when it's being cooled, it will be contracting. But when it reaches 4 degrees Celsius, it will expand instead of contracting. So it will be expanding till it reaches 0 degrees Celsius. Then it should continue to contract and change states.
Okay, so we talk about anomalous expansion because when it's being heated, we expect a continuous expansion, but at a particular temperature range, instead of it expanding, it will be contracting from 0 to 4. Then when it is being cooled, we expect a complete contraction of water. This norm will be obeyed, okay, But at 4 degrees Celsius to 0, instead of it contracting, water will be expanding. And this also explains why ice floats on water. Why ice floats on water? Ice floats on water because, you see, ice starts at temperature of 0. So at 0, we have water and ice plus ice in coexistence. Change of state starts from 0, and the temperature must be maintained. So from 0 till we have 0 complete ice. Okay. Let me pick it from 4. 4 degrees. At 4, water is contracting instead of water is expanding instead of contracting. So from 4 to 0 degrees water, change of state starts. At 0 degrees, we have ice plus water. Okay, this temperature 0 must be constant till every water has turned to ice. So look at it. By the time we have complete ice, because water is within its abnormality or unusual state, which is expanding, by the time we have complete ice, it has expanded from 4 degrees Celsius to 0 degrees complete water, complete ice. And since its volume is increased, we expect the ice to have a density which is less than the density of pure water. Because at 0 degrees ice, water has completely expanded. And so if it has expanded, then its density must be less than the density of. This is the reason why ice floats on water, due to the anomalous expansion of water. Please, is that okay?
Yes, please.
So
Yes.
that is the whole essence of anomalous expansion of water and how it's beneficial to aquatic lives. So the 1,000 kilogram per cubic meter, which is the density of water, is actually density at 4 degrees Celsius. But the point is that at any other temperature, the change is very, very small. That is why we have taken that as density of water, irrespective of the temperature, unless the temperature is severe. But at room temperature, which is about 24 degrees Celsius and all that, we take the density of water to be 1 gram per cm³ or 1,000, because the variation in density is very, very small. So we take the at normal, unless at a very high temperature, where we take account of the massive temperature involved. So that's it. All right. If there is no other question, then I'll send you expansion in gases, not so difficult. Just as I gave you in expansion of liquids, I'll give you a very well-crafted notes so that we will look at calorimetry and all that in our next meeting. Okay. Now, and within the week, I'll be sending you work sets on expansion of liquids and gases as well, so that we can figure out how to answer questions with that. So we'll continue our lesson once again next week. Please, may the good Lord be with you. Assignment, please, please, please. Whenever you are giving assignment, try your possible best to do what you can. If you find it difficult or in answering, you get back to me, okay, by WhatsApping. I'll respond to you and guide you. Okay, let's try and then, apply whatever we learn in answering questions. So we'll continue from next week. Take care of yourselves and bye-bye.
Hi.
Bye.
All right.